let's go ahead and get started. Again, just a quick overview of the logistics. Feel free to be using that Q&A, chat in those questions. I can take some questions at the end. I also have a colleague on the line who can chat back to you and answer some of the more simple questions. In terms of the best view, be sure to be looking at both the slides as well as the camera. I have lots of cool metal parts with me here today that I'm going to be talking about throughout the webinar. And then again, I do just have one quick poll that I'll share the results with all of you immediately, just to get a better understanding of who I'm talking to. Today, we're going to be talking about AM versus casting. My name is Ethan. I'm a technical marketing manager here, and I'm excited to talk about this topic with you all today. Quick agenda for today. We're going to start by looking at what some of the current challenges are in the casting industry and how additive can potentially add some solutions there. We'll talk about this transition that's happening in the industry from additive 1.0 to this new idea of additive 2.0. We'll look at desktop metals printing technologies and how they allow for this idea of additive 2.0. We'll then look at metal 3D printing as a complement to casting, where we'll talk about prototyping, pilot runs, and replacement parts. And then we'll look at metal 3D printing as a replacement to casting when we're talking about tooling-free manufacturing and new design features that are now possible in high volume. We'll also briefly look at properties of printed parts and how those compare to their casting alternatives. Real quick, just to give me a better idea of who I'm talking about today, I'd love to do this quick poll. How are you currently making parts today? You know, I'm sure many of you are doing a lot of these different methods, but I'm curious to hear, how are you making metal parts today? Hopefully lots of you say casting, considering this is a webinar for casting, but I'm curious to hear what manufacturing methods are you using today? Over 200 people on the line today, so we should get a pretty good distribution of how people are making parts today. All righty. Give this a few more seconds. Already got a lot of votes in here. All right, I'll wrap this up in just 5 more seconds here. Cool. So let me share the results here. Very, exactly kind of what I expected. Lots of people making parts with casting, which is great because that's what we're talking about today. And then, of course, machining. Machining is one of those very, very versatile manufacturing methods that I'd be surprised if almost all of you weren't using machining to some capacity. Good to see that some people are familiar with metal 3D printing and are using it today. And of course, we're going to talk a lot more about metal 3D printing today. Let's go ahead and get started. So, casting. Casting is a very popular manufacturing method. It's great for these complex shapes that are generally, difficult or uneconomical to make with other methods. It's also a great manufacturing method because it can be used across a wide variety of different volumes, from low volume with things like sand casting and even investment casting, all the way up to very, very high volume die casting operations where you're producing even millions of parts per year. And you can see on the screen, it's great for these very, very complex shapes with some of that organic curvature and a variety of different geometries. Of course, we do consider casting a traditional manufacturing method, and it does carry some challenges with it. Whenever we're talking to a foundry or a customer who is doing lots of casting, we hear these same challenges coming up over and over again. Long lead times, generally 8 to 14 weeks to get parts back from the foundry due to these tooling lead times. Of course, associated with that tooling are these very large non-recurring engineering costs, both in the design of that tooling as well as the fabrication. And sometimes it's just the design of that entire process from your actual drawing to the end use part that may have to go through casting as well as post-processing processes. Also, it's a very industrial process. So of course, I'm gonna be surprised if you're not a foundry, it's not very common for you to be doing casting in-house, which means you have to put your trust in the hands of this third-party foundry who you're using. The result of these challenges is you're generally seeing months to bring up a production line. From the day that the PO is signed with the foundry to you start getting parts back in-house, you're seeing months in between that period of time with a very long lead time. You're seeing a lot less design iteration because of this, because once you finally sign off on that finalized design, you're not going to be able to easily make changes to your design because now the foundry is designing all the tooling around that specific geometry. I kind of like to, at this point, I kind of like to say you're bending to the will of the manufacturing method, but we see a lot of people who are sacrificing design optimization to allow for ease of manufacturing. Or there may be a design that may be more optimized for your actual application, but you can't justify doing that design because it would make it more difficult to produce that part via casting. And lastly, casting for some methods, especially with die casting, you're seeing only very high quantities able to be produced because you need to amortize that tooling cost. You need to produce many parts in order to justify that investment into the tooling. And while today, we're talking about casting, of course, these challenges are really true for, a wide variety of traditional manufacturing methods, from volume machining to powder metallurgy like press and sinter and the MIM applications, where we're seeing very similar challenges and very similar results with these months to bring up production lines, far less design iteration, and of course, you're the sacrificing of design optimization to allow for ease of manufacturing via traditional manufacturing methods. Of course, today we're going to be talking about how metal 3D printing can alleviate some of these challenges and what some of the results are from doing that. We're going to split this presentation into two different sections. The first section is going to be metal 3D printing as a complement to casting. Of course, metal 3D printing is not going to completely, eliminate the casting industry, an industry that's been around for hundreds of years because we have some new metal 3D printers. For many parts, it'll still make sense to cast them, but metal 3D printing can still add lots of value as a complement to that traditional method. But for a wide variety of parts, it will make sense to actually replace the casting method with metal 3D printing, depending on the geometry and the volumes, of course. So the second section of this presentation, we're going to be talking about metal 3D printing as a replacement to that traditional casting method. Like I mentioned, as we're talking about that complement to casting, we're more talking about low volume applications. We're talking about replacement parts for parts that were traditionally cast, pilot runs for when you're in that product design stage. Maybe there's some specialized orders where you can't justify producing parts via the casting method. And of course, that prototyping stage where you haven't invested in tooling yet, you haven't done the NRE costs to produce those parts via casting, but you want to produce those parts in metal, seeing lots of value with metal 3D printing as a complement to casting. When we go on to talk about metal 3D printing as a replacement to casting, we're more talking about high volume, and we're talking about the ability to mass produce parts via binder jetting. We'll briefly talk about how binder jetting works and how it allows for high volume, but for many part geometries we're going to look at today, you actually see them being replaced with metal 3D printing because of this great benefit to produce parts in high volume without the need for any tooling. Before we jump into the desktop metal products, I briefly want to talk about this concept of moving from metal additive 1 to metal additive 2.0. Metal additive 1 really revolved around these laser powder bed fusion machines that produce parts with a laser that was scanning on top of a layer of metal powder. We like to make this comparison that these powdered metal 3D printers, these laser powdered metal 3D printers, are very similar to what a 1970s punch card computer looked like. They were these very, very large machines. They took up entire rooms. They had these highly trained special operators that you would submit your jobs to. A few weeks later, they would bring you back the results. That's really how we feel laser powdered metal 3D printers are today. They're stored away in the back rooms of your office buildings or your labs. They have these highly specialized facilities with ventilation and explosion-proof rooms. They have these highly trained operators that are very difficult to run these machines. And to the everyday engineer, to the everyday designer, this technology is really not accessible. It's not at your fingertips. So this is really how we feel laser powder metal 3D printers are today. And these challenges really led to a variety of limited applications. These applications really revolved around applications that were able to justify these very, very high part costs and the slow processing times that were possible. Generally, they were very, very specialized, not cost sensitive, and almost always produced in low volume. You saw many applications of powder bed fusion machines in aerospace and medical device, mostly because they could stomach these very high part costs, and the quantities were almost always in low volume. Here at Desktop Metal, though, we feel that metal 3D printing has barely scratched the surface of what's possible. For prototyping and tooling, generally it's been a too industrial and too expensive process to justify. And then when it comes to volume production, it's just not fast enough or cheap enough to justify producing these parts in volume. But this additive manufacturing industry is really at this inflection point where it's time to move on to the next stage of additive manufacturing. And it's what at Desktop Metal we're calling this idea of additive manufacturing 2.0. Additive manufacturing 2.0 is going to be producing these repeatable, high volume, cost competitive solutions that have the finish, accuracy, properties, low cost, and speed that's similar, comparable, or exceeding that of traditional manufacturing method. This idea of additive manufacturing 2.0 is really driven by these main two themes. The first being accessibility. These systems are becoming far more accessible for the everyday engineer, for the everyday designer to get their hands on. So now parts that may have been too expensive or too difficult to print before can now be justified thanks to these lower cost, accessible, easy to use 3D printing technologies. A lot of the parts we're going to look at today, the geometry is, well, it's somewhat complicated. It's not, absurd to think that you could easily machine this component, but in many applications, it makes more sense to simply throw it on the printer and in a few days you have your part rather than having to design, your fixturing as well as the CAM programming to actually produce this part via machining. The second side of this is the idea of high volume manufacturing. Metal 3D printing really used to be this very niche manufacturing process that was only used to produce maybe one or a handful of parts for these very, very specialized applications like we talked about. Today, we're starting to see that really accelerate into higher volumes where you can now print hundreds of parts, thousands of parts per day, where you can actually go to market in metal with metal 3D printing. And we're going to look at a ton of examples of that today, especially with how that compares to casting. To introduce Desktop Metal and how we're making this mission possible, Desktop Metal, our mission is to make these industrial grade 3D printers accessible to all engineers, designers, and manufacturers. Our promise is to produce printers that are cost competitive, high speed, and have this exceptional quality 3D printing, quality that you need and expect for your end use applications. To date, we have 4 metal 3D printers, and our solutions are designed to compete with traditional manufacturing at any scale and any level of complexity. On the bottom here, you see the Studio System, which you can see just over my shoulder here to my right. The Studio System is great for these prototypes, one-off parts. It's very, very easy to use. It's a very, very safe system. It does a great job of competing with machining, laser powder bed fusion for these prototypes, one-off parts. We're going to look at a bunch of examples and how that compares to the casting industry and where the Studio System is adding value there. When we want to move to higher volume, we're going to be talking about the binder jetting systems at Desktop Metal. These systems, you can see the shop system just over my shoulder here to the left, really allow for much, much higher volume, producing hundreds or thousands of parts per day, over millions of parts per year with the production system, really designed to compete with traditional manufacturing methods when it comes to volume. So how do these systems work? At Desktop Metal, we chose to design our printing systems around the chemistry and supply chain of metal injection molding. I saw, when we did our poll that some users were familiar with metal injection molding, are using it today to produce parts. But for those of you that are not, metal injection molding is this powdered metal process that enables you to create these very, very complex shapes and then mass produce them utilizing these inexpensive metal powders. It has these widely accepted standards, both ASTM and ISO standards, and has a broad range of different materials available, from stainless steels, even titanium and copper are possible with this metal injection molding process. It's used across a wide variety of industries, everything from automotive to the firearm industry, even the medical device industry, to produce these beautiful parts in very high volumes, utilizing these inexpensive metal powders. These powders enable you to create these complex parts with quite excellent metallurgical properties. If you look at our chart here, you can see that top kind of L shape showing what a wrought material would get in terms of ultimate strength as well as elongation. And just below that is our powdered metal MIM parts, which are, still excellent material properties and really fall just below that of a wrought material. How does this process actually work? You start by mixing a metal powder, that's our low-cost metal powder that we talked about, with a binder into a feedstock. You're then going to inject this feedstock into a mold the same way you would in a plastic injection molding process to create what we call a green part. That green part is still that combination of metal powder and binder. It's quite fragile. You could break it with your hands, but our part's taken its shape. It has metal powder and it still has that binder to glue material holding it together. From there, we put it into the debinding system. That's a solvent wash. It's going to remove most of the binder out of your part, and then you put it into the furnace. The furnace is going to get just below the melting temperature of the material, and it's going to sinter, and it's going to remove that last bit of binder from your part and actually sinter your part into a dense, strong metal part. Sintering is a process that allows you to fuse your metal particles without actually melting them. So how do our systems compare to this process? Of course, with MIM, like we just mentioned, you have those 4 steps, but what's the main challenge with this MIM step? The tooling, of course. With this process, for each different geometry you want to make, you're going to need this different expensive mold that's going to be the shape of your part. Of course, we utilize these same materials, but we remove that tooling step. When looking at the studio system, rather than having this loose metal powder, we create our feedstock in a rod. This rod is extruded through the nozzle of the printer. We're going to build up the part layer by layer to create, the same thing that would come out of the mold in what we call a green part. Again, this is that combination of metal powder and that polymer binder. It's pretty fragile. If I drop this, it would break. But here we have our general shape of the part with that metal powder held together with that binder material. After that, we're going to put it in the furnace. You can see the furnace directly here behind me. That furnace is going to remove that binder material. The part's going to shrink about 20%, and we're going to end up with a dense, strong metal part here. Hopefully you can hear that. Oh, for some reason, I just lost my screen. One moment. That's strange. My monitor turned off for some reason. Oh, 1 second. Sorry about that, folks. Hopefully, sorry about that. Not sure why that happened. Okay. Nick, does everything look okay now? Sorry about that, everybody. For some reason, my monitor decided to switch off.
All good.
Okay, sorry about that. Anyways, so after that sintering step, we end up with our dense, strong metal part like you see here. Now we have a dense, strong metal material, but of course we've been able to remove that tooling step. We don't need a different mold for each part we want to create. If I want to print this today and I want to print this pulley tomorrow, all I have to do is upload a different file and hit print on the printer. When it comes to the binder jetting machines, we use the same metal powders that we're using in the studio system and metal injection molding, but now we're actually jetting our binder onto that metal powder layer. We're producing hundreds of parts per day because we're able to droplet binder over that entire area-wide bed. We'll look at some animations of this later that make it a little bit more clear. And then that same step where after the printing step, we put the parts into the furnace, but now we're able to print hundreds of parts at a time in these large batches. We'll look at some animations later that make it a little bit more clear how that process happens. So quick review of the benefits here. Studio system, it was really the world's first office-friendly machine. My desk is right across the room here. I sit across from this machine all day long and I print parts all day long. It's great for those low volume applications, prototypes, jigs and fixtures, tooling. Very safe for the office. You're never exposed to any powders because we're using these rod materials. We have this very easy separable support process that allows your supports to easily come off of the part. Easy automation. The software is going to walk you through the whole process, and easy to change materials. The materials come in these cartridge systems that just swap in and out the same way you would an inkjet printer to allow for very easy material changes. Shop system, which is the other machine that you can see over my shoulder here, really the world's first binder jetting system that's designed specifically for machine shops. It's designed to go into machine shops. It's great for this batch production of end-use parts, very high throughput of hundreds of parts per day, still very accessible. We're going to provide everything you need to get up and running with the shop system, very high print quality, and it produces these fully dense isotropic parts that are great for these end-use applications where you need those great material properties. All right, so that's a little introduction to Desktop Metal, a little bit of an introduction into this idea of additive 2.0, but now let's look at a bunch of examples and let's look at our two main themes, starting with this idea of metal 3D printing as a complement to casting. The first thing we'll talk about is using metal 3D printing for your prototyping and your pilot runs. With either of these machines, here we're going to be mostly talking about the studio system. You're able to print these functional metal parts quickly and affordably during the development stage. You can print batches of parts as well to allow you to validate the design across multiple units before placing this casting order, before investing in this non-recurring engineering time and waiting that 12 to 14 weeks to get your parts back from the foundry. These parts can now be tested under high loading, high heat, even corrosion environments, where we're no longer just printing parts to test our form and fit, where we would do in plastic, where we print a PLA or an ABS, and we say, does this fit in our machine? But now we can actually run our machine under high heat, loading environments, corrosion environments to understand, do these parts actually perform before we move to a casting environment? The first parts we're going to look at is some parts from this worm gear speed reducer, a very common machine design component used to either increase speed or increase torque. The first part, I have here printed on the studio system in 4140 steel. Obviously a very common mechanical component. If you're, I'm sure many of the engineers on the line here today recognize this worm gear component. Eventually this part is going to be produced via casting and then followed by a hobbing operation. But, with the studio system, we're able to test a couple different designs. We can vary the pitch, we can vary the dimensions of these teeth to understand really how this part's going to perform before we move to these higher volume applications. So, I can print a wide variety of these. These were printed on the studio system. We can test these parts functionally before we move to the casting and hobbing stages. On the studio system, this part can be printed for just $86 compared to, when you're looking at outsourcing this for maybe a machining prototype, it's going to be over $390. So the ability to produce this in-house, both cost savings as well as accessibility and lead time savings of being able to produce this part. From that same assembly, there's also this front mounting flange. Of course, this is a great example of a part that's eventually going to be cast. They're going to mount your motor or your output shaft to this flange to allow it to, in your worm gear reducer. But again, before we move to that casting stage, we want to print this part to prototype it. We want to understand how it's going to perform. We want to have a functional part to test. So again, we may have wanted to print this in multiple different geometries with different ribbing, with different hole patterns to allow for different motors and different outputs. And now we can print this part quickly, affordably, and the ability to iterate on this part without having to move to casting. Again, printed in 4140. This is actually a scaled down version compared to what you're seeing on the screen, because again, we printed this part in a variety of different sizes. The large one that you're seeing on screen printed for just about $420, but again, to outsource that part for machining of this prototype was going to be over $1,000. So still, a huge benefit here printing this part. Another pump housing, another example of a part that's going to be cast in high volumes once we finalize the design. You can see it's the front housing here of that pump. It's part of a hydraulic pump. When it's produced in high volume, this part's going to be cast, followed by some secondary machining operations. But of course, by printing this part, we're able to avoid the long lead times of casting if we were to produce the prototypes via casting, as well as the lead times of machining, both from maybe our internal shop, as well as having to go out of house to have this part to be produced. It can be produced for just $228. To outsource this part for machining was going to be over $710 or $708. So just another great example of a geometry for when we are going to move to casting that we can now quickly print for our prototype. Faucets. We work with a variety of different faucet manufacturers that are always looking to iterate and test different designs. Before they move to high volume, they want to produce these parts. They want to actually install these parts. And they want to understand how they look, how they perform before they move to these higher volumes via casting or other manufacturing methods. You can see, a great example of a part here that's been printed. It's then been polished with, of course, these parts after they come out of the furnace are metal. They're fully compatible with your traditional finishing operations. This has had an isotropic super finishing done to it with some chemicals and an abrasive media to give it that nice shine to allow it to be tested to see, is this the part that we want to go to high volumes with? Another example here is this gear. This is part of a crankshaft gear assembly. This part actually attaches that crankshaft in a motorcycle engine to the water pump, as well as the oil pump to actually drive those two pumps off of the main power off that crankshaft. This is actually a good example of assembly consolidation where we're able to, this part was originally manufactured as two different separate gears that were then welded together. But with 3D printing, we're able to consolidate those two gears into one part and print this geometry all together as one. Again, very, very easy to prototype this component on the studio system. And then when you move to production with casting, followed by gear hobbing, similar to the last gearing we were looking at, we've already validated our design. We've already functionally tested it in high heat, corrosion, high loading environments, where we've been able to run this part at high speeds to understand that this is the geometry we want to move to mass production with. Some pumping components, valve bodies, of course, similar to the pump housing we were looking at earlier. Valve bodies are a quite common cast component, but before we actually move to the casting stage, it's beneficial to be able to prototype these parts. This part's part of a valve body for a block and bleed valve. Has some channels that would be very, very difficult to machine, if not impossible. But of course, printing this part on the studio system, you can print this part in just a couple of days in 316L to give it that nice mechanical properties and corrosion properties from that 316L stainless steel in just a few days before moving to these higher volumes of casting. Again, produced for just $88 in just a couple of days. So just trying to give everyone a bunch of examples here to give you a better understanding of some of the geometries that are really beneficial to print. Looking at our first customer of the day, EWOL. They are a manufacturer of high-tech marine propellers, and they are located in Milan, Italy. Founded in 1997, like I mentioned, they produce these propellers as well as propeller components for these very, very high-end sailing yachts, and they use a wide variety of stainless steels to give them this excellent mechanical performance as well as corrosion resistance and mechanical performance. Of course, this is a lot of these parts are in the water, exposed to seawater, salt water, so they want to have that excellent corrosion resistance as well. The first part we're going to look at is this propeller pinion. This part actually connects the propeller shaft to the actual blades. The goal for EWOL was to streamline their manufacturing. Traditionally they were making this part via an investment casting process at a 17-4 stainless steel, but it was coming with lots of hassles, lots of logistical issues. So the project goal here was to overcome the investment casting manufacturing constraints and produce a part that they could actually produce to move into end use parts with. So the first issue that they really faced was this casting lot size issue. And I'm sure many of you on the line, whenever I'm talking to a customer who's casting parts, they always talk about this issue of lot size, where they have to place a minimum size order, otherwise they can't justify or the part costs are too high. For them, that was 100 pieces. If they weren't ordering a minimum of 100 pieces, the part cost was too high or the foundry wasn't willing to do it at all. On top of that, even after they've collected enough components, there was a very long lead time associated with these parts. Of course, investment casting has this alloy procurement, wax pattern setup. Investment casting is just a relatively long process. So even after they placed the order, there was quite a long lead time. When the parts came back from the foundry, they still required this challenging labor-intensive CNC machining operations. They had to do these inner ribs and that bottom kind of coupling component, and that cutting tool needed to go deep inside the inner diameter of the part and had limited access. So what do? They took their model and they started to print them on the studio system. You can see there on the left, on the right side of that left image, you can see the part that's come right off the printer. And on the left is the part after sintering. You can see it's got that strong, dense stainless steel material. They still had to do a little bit of post machining to the component, but of course, these parts are going to perform the same way when machining as a raw material would, very, very similarly. But with printing with the studio system, big business impacts for EWOL. They're able to be much more responsive to their customer demands because they're not having to wait on this foundry. As soon as an order comes in, they can load it on the printer, they can print the part in a couple of days and send it out. They're finding it as a much faster manufacturing process with reduced health hazards, of course, because it's a very, very safe and easy to use process, less demanding in terms of logistics because they don't have this lot size constraint. They're actually able to lower the part cost, improve the part quality they found over their investment casting alternative. It's a much less labor intensive process and much more sustainable process than casting, which was important to them. So big business impacts for EWOL, this ability to produce these complex geometries for improved performance and manufacturability when it comes to these replacement parts and these prototypes. This project really demonstrated the feasibility of additive manufacturing as a truly possible manufacturing method when it comes to speed, flexibility, quality, and cost to be considered across a wide variety of their other parts. The next step for them is really to explore what we're going to be talking about in the next section here, which is moving to volume production with high volume parts via binder jetting, specifically with the shop system, where they want to, try to eliminate this casting process altogether and actually just print these parts in high volume via binder jetting. The next section is talking about replacement parts. Many parts have these lifetime service agreements where companies have to either, warehouse components or keep manufacturing lines up and running or find these alternative manufacturing methods to ensure that their customers always have replacement parts when and where they need them. Many industrial machines come with these lifetime agreements that whenever they need replacement parts, they're going to be available for them. Of course, 3D printing is an excellent alternative for producing these parts because now we can do what's called a digital warehouse or a digital inventory. I can keep a simple file on my computer, and whenever that part's needed, I can load it onto the printer, and in a couple of days, I have my end-use part ready to go, ready to ship out, ready to get deployed in the field. The first example we're going to be looking at is this brake housing. You can see the cast alternative there on the right, and then you can see the part that was printed on the studio system as a replacement. You're seeing very, very similar looking geometry, very, very similar looking surface finishes and material properties. So this is a brake housing. It's used to integrate multiple different moving components on an excavator machine. At one time, of course, this part was produced in very, very high quantities, but this part's no longer in production, but there still is a small trickle of needed parts for replacement parts for those, those people who are still using machines that operate this part. In those examples, it's far more affordable to produce this part with 3D printing than, of course, to keep that manufacturing line up and running. This part was produced in 4140. It's one of the early on parts we produced here at Desktop Metal. If you've been around for a while, you've probably seen this geometry before. It has a little bit of oxidation on it just because this is a 4140 low alloy steel component. But great example of a replacement part where when the customer needs it, we throw it on the printer. In a couple of days, we're ready to ship it out into the field. We can print this part for about $1,000. It is quite a large geometry, but to outsource this part for machining is going to be over $2,400. So still a huge savings, as well as a time and just logistical savings of being able to print it on our own machine rather than having to go out of house. Looking at another customer who's making use of printing for these replacement parts is this company, Master Drilling. They're located down in Johannesburg, South Africa, and they are a manufacturer of these very, very large earth drilling machines. They drill, miles into the ground, mostly for these mining operations, oil and gas operations, and they produce these very, very large machines to do this actual drilling operations. The part that we're going to be talking about today is this sun gear. This sun gear is the sun gear of this planetary gear set. It's used to attach this very, very large motor that you see. It goes through the planetary set, and then of course to the actual drill bit that's doing the drilling miles into the ground. You can see it actually being installed here. You can see the part that they printed here. Unfortunately, with their original part, they were casting it in a foundry in China. When they had one of these parts break, they found they had a 3-month lead time to get this part replaced from the Chinese foundry. Of course, they did not want to have their drill down for 3 months, so they were looking for an alternative. How do we get this drill back up and running as fast as possible? By switching over to the studio system, they were able to print this part in just 3 weeks. So what did that 3 weeks entail? It entailed printing this part. It did have to go through a debinding step because it was using an earlier version of the studio system. They then sintered this part into the furnace. They did a case hardening operation to actually bring up that hardness value on those teeth to ensure it had a long lifetime. And then they did some post machining to ensure that it was hitting all the critical dimensions that they needed. It's quite a big part. You can see the results there on the bottom, that after printing, they had about a 25 Rockwell. After that heat treatment process, the first heat treatment, they got up to 43. And then after a plasma nitriding, which really helps to increase that hardness on the surface, all the way up to a 64. But a great example of a part that was originally cast, they needed a replacement. So what did they do? They went to, to their studio system and was able to produce a part going from 3 months down to just 3 weeks. This next part here is a thermostat housing. Sorry, I lost my monitor again.
You can still see your slides if you want to keep going.
Yeah, I just don't see them. It's all right. So I could do it without the slides. This is a thermostat housing. This is used on a vintage Mercedes-Benz engine that is no longer in production. Of course, vintage cars is a great application. Many people are still working on their cars. They still want their cars in production. So to replace those components, 3D printing is a great example. You can see this geometry here, able to simply, they found that in this example, they actually found the original part. They're able to scan this geometry and then load it up onto the printer, and in a couple of days, produce their part. Just jump around here. I'm just gonna switch over to just my laptop. Sorry, folks. Just 1 second. Okay, dokie. Sorry, I had a second monitor here, but it doesn't seem to be working. So we'll just go off just the laptop, which is fine. Anyways, thermostat housing. Again, this is part of the cooling system on a vintage Mercedes-Benz engine. Part was originally cast in high volumes many years ago, but now, of course, that supply chain has dried up. When replacements are needed, they were able to find the original part, scan the geometry, upload it to the printer, and in just a couple of days, they had their volume part. So it's a great example of an aftermarket replacement part here. This part was produced in 316L to give it that excellent corrosion resistance that's needed for those high volume, for those corrosion environments, because there is some steam and some other corrosion fluids being involved here, produced for just $99 on the Studio system. You can see a couple examples of it in context here on that actual, in that actual assembly that's going to be produced. See, and then again, you can see that example of it after being polished. That was polished with this isotropic surface finishing process to give it that really, really nice, clean finish that some people need for those aesthetic applications. The next customer we're going to be looking at is Zink Hamworthy Combustion. They are a leader in emissions control and clean air combustion systems, located in Oklahoma here in the United States. They, had this additive manufacturing initiative they wrote on 2016, where they're really looking to increase the amount that they're using additive across all of their product lines. They were using some plastic 3D printing. They purchased a desktop metal studio system and started printing parts in metal. What are they using their studio system for? They're using it a lot on their manufacturing floor for jigs, fixtures, custom tools, and dies. Not something we're going to talk too much about today. We have lots of other webinars that are talking about using the studio system on the manufacturing floor, but they're using it a lot for those applications. They're also using it a lot for these urgent aftermarket orders, which is why we're talking about them today. Parts that they need to produce sooner than what they could receive from their casting suppliers. So we'll look at a couple of different geometries that they produced that were parts that were originally cast that now they're able to produce on the studio system. They're also looking to prototype parts for testing purposes. They want to be able to produce multiple parts very quickly to enable them to get to market faster. And then they're also actually making use of some of these geometries that just cannot be manufactured with traditional manufacturing methods. They have these very, very organic shapes as well as some internal channels to really increase the performance of the part, but they just can't be produced any other way besides additive manufacturing. First example here is some parts for the USS Blue Ridge. These parts were originally cast. They're these yokes and handles for this safety shutoff device. When some replacements were needed, when some more parts were needed, of course, that casting line was no longer operating. What do? They grab their part. In this instance, actually, they only had a drawing. They grabbed their drawing. They very quickly modeled up the part, loaded up on the studio system. In a couple of days, they're ready to send them out, get them deployed on that ship. You can see the printed parts there on the right, a couple of different geometries that were very, very easy for us to print, but would have taken weeks, if not months, to produce via casting. Another example here is this YE6 burner tip. That's the part that I have with me here today. This is actually a combustion engine component that was originally produced in 1967. If you look at the drawing on this part, you can see that approval date from Neil back in 1967. They needed to produce a replacement of this part, but of course the manufacturing line was no longer up and running. The part was originally a cast component. They found this original print in some file cabinet, way in the back of their office. They're able to, model up this part quickly, and then they got it loaded up on the studio system, and in just a couple of days, got this geometry printed, and they were able to deploy it out into the field to their customer. So allowing them to be much, much more agile with producing these replacement parts than what it would take to spin up a casting line for these examples of parts that were originally cast, but now we can replace them with printed parts. So big business impact for John Zink. They introduced this low-cost metal 3D printing option that's actually able to compete with casting, compete with machining. They can take these new designs to market faster because they can test these multiple different designs and iterations without tooling. They're avoiding any tooling costs for these low volume parts, and they're seeing a much faster turnaround from printing than they would do from casting. So now let's jump over to this next section, that's metal 3D printing as a replacement to casting. The main challenge that we've already briefly talked about with casting is this idea of the ramp up. From when your drawing is approved, when the PO is approved, you're seeing these very, very long foundry lead times and these high non-recurring engineering costs. Much of this comes with the development of the process and the development of the tooling, either the mold tooling or those match plates for these casting processes. 8 to 14 weeks of lead time, as well as these large non-recurring engineering costs. The result of this, as we mentioned earlier, far less design iteration, far less optimization than you would want for these components. So what does the setup process look like for casting? Generally it's, like we mentioned, this 4 months. For investment casting, you have to do this mold design, get this approval from your customer, do some iteration as well as the actual creation of that mold, which is quite a long process. When it comes to investment casting, you then have to do the injection, the slurry coating, the actual knockout, then this casting, as well as the post-processing process. That all in all, you're seeing about 14 weeks of prep before any parts are actually being produced. Now what happens if the design changes? We've already invested in this tooling, we've already invested in this molds. Now we have far longer times, a very long lead time to make a simple change to our geometry. If possible, we could make some small changes to the mold, but generally we're seeing very, very long lead times to make any changes to our geometries when these parts are being cast. How does this compare to a binder jetting process? In binder jetting, we see about 1 to 2 weeks to get up and running. You have to, get your part in, you maybe do some generation of some ports, you do some scaling, some simulation to understand what the shrinkage of that part's gonna be. You then print that part, depowder that part, sinter that part, and in just 1 to 2 weeks, you can produce hundreds of parts. Whether or not when those parts are adequate, they're coming into the furnace the way you want them to, you can then immediately turn that machine on to start producing thousands, tens of thousands of parts per week without the need for any tooling. So of course, we're shrinking that 4-month timeline down into just 1 to 2 weeks. Of course, now what happens when the design changes? Let's say we want to change the diameter of a hole, or we want to add some features to the geometry. Now, instead of having to go all the way back and make changes to our tooling, all I have to do is upload a new part to my binder jetting machine, and in a couple of days, I can have hundreds of that geometry in hand, allowing me to be very, very flexible, very, very, very agile with my manufacturing process. So binder jetting really allows us to do this mass production without tooling. You can see a wide variety of different geometries here. We're going to talk about a lot of these parts today, but binder jetting allows us to actually mass produce metal parts without the need for any tooling. What allows binder jetting to be this key technology for mass production is this ability to have very, very high throughput thanks to this area-wide raster-based printing, where we're printing over the entire area of the print bed in one pass. We're still utilizing these low-cost metal injection molding properties thanks to this very, very established metal injection molding supply chain that already has these broad range of materials that are already being used in the metal injection molding industry. The parts come out of the furnace with these isotropic material properties because we're heating the entire part at the same time up to temperature. We can use these very, very large scalable build boxes that allow us to print a wide variety of geometries at the same time, or the wide variety of, or a large quantity of the same part at the same time. And again, very, very low waste process because we're able to reuse any material that's not printed during the process. Of course, there's various different production scenarios. This is looking at the build box for a shop system. You can see on the left where we're doing, very, very customized runs. We're able to mix a wide variety of different geometries all together in one simple run to run all these parts at once, producing hundreds of geometries overnight. When we need to go into a little bit of higher volumes, where we want to produce maybe 50 parts at the same time, I can batch, a bunch of different geometries together, but still produce many of these parts at once cost effectively. And then when we want to move to actual volume production, I can batch all of these parts together and just run serial volume production, allowing me to print, hundreds of parts at once for our end use applications. First part we're going to be looking at is this bracket parking shift. This is part of a parking brake assembly in a car. Of course, this part would have required some very, very complex dies because it is being produced in high volume. That only die casting would have been the alternative because those high volumes that parts being produced in. Production system, of course, eliminated the need for any tooling for this part, allowing you to produce this part on demand in as high as volumes as you need because our part cost is going to stay flat. For this geometry, part can be produced for just $4.71. You can do over 340 parts per build, over 500,000 parts per year. So you can see with binder jetting, we're really starting to move to higher volumes where we're not just printing one-offs, prototypes, replacement parts. Now we're actually replacing our casting method with binder jetting. This rocker arm, this is the part I have with me here. It's used for opening and closing the intake valves on an outboard boat engine. This part, to ensure it had that adequate strength that needed to be produced in this 316L steel, thanks to that extra corrosion resistance that's given by that material as well. Printing allowed us to add, these ribs that were needed to add any extra material to really allow us to optimize this geometry rather than just optimize it for the casting process. You can see the cast alternative on the left there, that sort of gray component, and then the printed part that I have with me here today. Again, this part can be printed for just $4.75 per geometry. Can do over 330 of these parts per build, over 570,000 of these parts per year. So again, really starting to compete with casting in terms of both cost as well as with the throughput. Another part here is the stator. It's used in, of course, a small electric motor. It's very difficult to justify the tooling on this geometry because it wasn't needed in that high of volumes. But in just one run on the production system, you could run all of the needed parts for this actual application and just cost, $4.48 per part. You can do over 274 of these parts per build, over 400,000 parts per year. We'll look at some actual build volumes here to give you a better idea of just how large these build volumes are and how fast these printers are. This is a joint here. It's a power steering joint. It's used to connect the actual electric motor in your power steering assembly to your actual steering wheel to give you that little assist you need so you don't have to be cranking on the wheel. This part can be produced for just $2.52. Can produce over 640 of these parts per build. One build on the production system takes just 4 hours. So you're able to produce over 640 of these parts every 4 hours. And then of course they still need to go into the furnace, but we're getting those really, really high volumes, over 1.2 million of these parts produced per year. Hopefully you can see the actual spline teeth on this part, but it's a really, really nice geometry that we're able to produce a really high volume at a really low cost per part. This next part is the seatbelt pulley, another automotive example. It's part of that reclining mechanism in a car seat seatbelt. Again, produced in 17.4. This part now we're looking at the shop system, which is the smaller binder jetting machine, but still very, very viable for batch production, mid-volume production, high volume production. For this part can be produced for just $5.86, over 793 of these parts per build, over 5,000 of these parts per week. So still seeing very, very high volume, very, very low cost per part, even on systems like the shop system. And you can see that build volume there, really allowing for many, many parts to be printed at once, overnight on that machine. Another example here, this lock plug, it's used for, an industrial door lock. Of course you put your key in there, the barrel would spin, align those pins with the pinholes on this lock. Again, produced in 17.4 for just $4.71. On this part, we can produce over 1,000 parts per build, over 9,000 parts per week, really allowing you to move to volume production with binder jetting. I'm going to go through a lot of examples here, but hopefully I'm convincing you that binder jetting really is an alternative for high volume production to produce these parts at a low cost per part, at a high throughput per week, or even per day. Another example here, this fuel swirler, really nice geometry here. This is used for pushing a fuel mix into a burner And then of course, still have that low cost per part, just $4.95 per part, over 600 parts per build, over 5,000 parts per week. Cool thing about this geometry, right, is let's say we make some changes to our fuel mix. We want to make some changes to our veins here. We want to add some veins. We want to remove some veins. Maybe we want to change the angle. All I have to do is make some changes to the geometry in my CAD file. It could be as easy as altering a circular pattern or one dimension in my sketch. Now I've changed my geometry to actually manufacture this part. All I have to do is upload a new file to my printer. And in a few days, I can have hundreds of these parts ready to go out into the field or ready to go into testing. The next geometry are these downhole tool slips. These are parts that are used in an oil and gas environment. There's actually a couple different geometries of this part that we're going to look at. They have some patent work going on. There's a lot of innovation on these parts going on. So they really wanted to stay very agile with this part, be able to alter the design on demand and not tie themselves down to some cast tooling. This is actually used for holding a frictional hold between a packer and a pre-existing pipe that's been drilled, used for oil extraction. I have a couple of different versions of it here, another model here. It's actually a consumable, so this part is lost after pumping is complete. So in keeping the price down was very important. You can see another version of it here. This one actually has two sliding components that are sliding within each other on this geometry. And of course, these parts were printed as is that still allow for that movement. So keeping the price low was very important. Able to produce these parts on the shop system, this binder jetting machine you can see over my shoulder here. The big win here was this flexibility. They can very easily change the geometry. They can very easily alter what this part looks like to allow for it to be high performance in different pumping scenarios. All they have to do is modify the CAD model, load it on the printer. In a few days, they can have all the parts they need for whatever pumping scenario they're in. Cost of this part, just $87 per part. They can do 26 of these per build, over 200 of these per week. So really allowing them to be agile while still keeping the cost low and the volume high. On top of that, when you're moving to high volume with 3D printing, we're now opening up all these new design freedoms that weren't possible with casting. You look at, original designs that are very, very generic. They may be blocky. We're really bending to the will of the manufacturing environment, but we're really trying to optimize our design to be easy to make rather than to be optimized. But with additive manufacturing, we can throw a lot of these design rules out the window, and we can really choose the geometry that's best for our application rather than what's best for manufacturing. You can see the new geometry there that's very organic, but we're dropping lots of weight on the design. And now it's actually possible to mass produce this part in metal with binder jetting systems. Of course, with lightweighting too, if this geometry were to be produced with traditional manufacturing method, of course, we wouldn't have lightweighted all those lattices in there. But with binder jetting, it's very simple for us just to simply core out all that weight, throw it on the printer, and I can print hundreds of these parts per day. And this actually reduces the cost of the part, right? Because now we're removing material out of the part, we're making it easier to print, less time to print, less material, that this part actually becomes cheaper to print via binder jetting versus if it was solid. Where really with any other manufacturing method, removing material, adding complexity like that would greatly increase the cost of the part. Another example of this is this, lightweighted bracket that you're seeing here. Again, after we finish the design, we think of how can we reduce mass in this part to be beneficial, to make it easier for us to print, less expensive for us to print, and also lightweight the geometry. All features, right, that would be impossible to do with casting, impossible to do with traditional manufacturing method, but is very easy for us to print. Again, this gearing here, you can see it features that nice complex lattice inside of the part. But now it's not just that we can produce one of these gears, it's that we can produce over 100 of these parts every 4 hours in the production system. So now it's actually possible to go to high volumes with parts that look like this, with geometries that look like this, allowing, in the next few years for you to see a lot more geometries that are highly optimized because now there's an affordable and fast way to make these parts. Assembly consolidation is another, of course, great benefit. So many parts today are designed for their manufacturing method, more so than they are their actual application. This leads to, assemblies with very simplified parts that are later assembled. Here's an example of a roller screw. You can see the original design was 7 different components. It had the main roller, it had the 2 gears on either end that were attached with these set screws. But with 3D printing, we can consolidate that entire assembly into just one part and print it as one simplified design. Of course, now we're not just talking about producing one of these parts, we can print hundreds of these parts at the same time on the shop system. Another example, mass customization, of course. We're not tied to any tooling now. We're not tied to any, set process that at any point in time, we can make changes to our design. So if our customer wants one design, another customer wants a different design, all I have to do is make changes to my model, upload it to the printer, and I can be very, very, very custom, be very, very, very customized to make sure that I'm doing exactly what I want my end customer to do, because we're not tied to any tooling. Like I've mentioned many times today, all I have to do is make changes to my CAD model, load it on the printer, and in a few days, I can have hundreds or however many my customer needs. This is an example of a gear shift knob. It goes on, of course, on your car gear shift. It can be mass customized with different textures, depending on what the customer wants or whatever the customer wants to design. And then I can actually mass produce these parts via binder jetting thanks to the shop system. This also has lots of benefits in the jewelry industry. You can see a couple of different jewelry designs here. This is a perfume ornament to really spice up a perfume bottle. Again, lots of design flexibility, lots of customization possible to allow me to really customize that design and then print them without the need for any tooling. A couple more examples here of some jewelry parts that you can see, really, really nice organic geometries would be impossible to produce with the traditional manufacturing methods, but now I can design whatever I want, print those parts. And these parts, of course, have all been plated after printing, electroplated. You can see, again, we're really moving to high volume too. We're not just talking about producing one of these like you would maybe with a wax process with some wax 3D printers where you would print your wax, then do investment casting. Now I can print hundreds of these parts, thousands of these parts at once to allow me to actually move to high volume with these nicely customized geometries. But how do these parts actually perform? So hopefully at this time, I've convinced you that metal 3D printing adds some value both when you're prototyping, your pilot runs, to help you complement your traditional casting methods. I hope I convinced you that for some geometries, for some volumes, it's a very cost competitive process for actually replacing casting. But a lot of you are probably asking, how do these parts perform? How do I know these parts are going to perform the way I need them to actually replace their cast counterparts? Sintered parts are composed of dense polymer-free metal. This is very important. After the sintering process, there is no history of that the part was ever powdered metal. It's been completely erased because we're able to raise that part slowly to temperature, to its sintering temperature, where we're actually able to have some grain growth. The grains have now grown larger than the original powdered metal particles were, and there's really no history that the part was ever powdered metal. It also has this homogeneous microstructure that allows the parts to be isotropic, where they have equal strength in all directions. 3D printed parts have this notorious stigma for being weaker in Z than they are in X and Y, but this is not true of sintered parts. Because we're sintering our parts, we're bringing the whole geometry up to its sintering temperature, allowing it to fuse in all directions, allowing it to be isotropically strong. It's this homogeneous microstructure and this isotropic part properties that make these parts very, very attractive for these industrial applications. So, our material properties really meet or exceed those standards that are set out by ASTM or MPIF standards. This is looking at a 17.4 stainless steel material where you're seeing a yield strength directly out of the furnace of over 650, 660 megapascals. Of course, the parts can still be heat treated if you want to. You get over 980 megapascals with that process. So you're still seeing these excellent material properties that you would need for these very, very industrial applications. Of course, all of our material property sheets are available on our website. So if you want to learn more, head over and download those sheets and you can see all these properties online. Looking at density on the studio system, the material density is really dependent on the actual material. For some of the carbon steels, we're seeing about 90, 94, 93.5%, looking to increase that constantly. But when it comes to 17.4 pH, which is the first material that we released on the studio system, we're now consistently seeing over 98% dense. So that density that you really need for your prototypes for those replacement parts. When it comes to the shop system and our binder jetting machines in 17.4 stainless steel, we're seeing densities 98% and higher consistently, giving you that really, really high densities that you need for those end use applications, for those parts that are going to be out in the field. And again, for all the materials we have available here at Desktop Metal, you can head to our website and you can download those data sheets to really get a better idea of the exact properties that you can expect with these parts. A quick example here of a part that was originally cast and then has been replaced with the shop system is this main gear. It's part of a smart control valve in the oil and gas industry, was originally made via investment casting. The reason that was moved to the shop system was they found that there's very, very comparable properties to casting, with the added benefit that they can make very, very slight geometry changes without having to move to any additional tooling or having to make any changes to the tooling. And after testing, it was actually found that this part outperformed its cast counterpart. This part was produced for just $18, can do over 114 of these parts per build, over 770 of these parts per week. When the customer went to test this part, they wanted to test this binder jet part versus their cast original. So this part needed to cycle 1 million times successfully and withstand over 270 inch-pounds of torque to ensure that this part was adequate to be deployed into the field. After looking at the testing results, you can see that the cast part was able to withstand 350 inch-pounds and the binder jet part was able to withstand 429 inch-pounds. So it really actually exceeded the properties of what the cast alternative was able to do. When it came to fatigue and cycling, the cast part was able to withstand these million cycles, but it had lots of deformation after the process was complete. When it came to the binder jet part, it passed, but there was very little to no deformation of the part afterwards, allowing it to be, could have withstand far more cycles than 1 million. So just a quick example of a part geometry that's, directly compared to the casting alternative, showing that it meets or exceeds those properties that are needed for, your replacement parts in the casting industry. That's all I have today. Sorry again about the couple mishaps there with my monitor and some of the technology. Hopefully it didn't ruin the experience for you. Thanks very much for joining me. Thanks for dedicating an hour of your day to me. Feel free to shoot me an email if you have any thoughts, questions, comments. I'm also, giving you this opportunity to sign up for a one-on-one discussion with me. If you are, currently casting parts, you currently think you have a good application for metal 3D printing or 3D printing in general, feel free to book a meeting with me. I love talking with everyone. I do a few of these a week. I always find them very valuable because I love talking to people to understand how you're making parts today and where metal 3D printing can potentially add value. I'm happy to take a look at some of your geometries to see what those parts would cost at our machines. I can give you that same costing, that same throughput values that we looked at today. If things make sense, we can produce some sample parts, send you some sample parts. So feel free to take advantage of that opportunity. I love to chat with everyone. So you can head to that link. It directly links to my calendar. You can set up some time for us to chat about your manufacturing environment and where metal 3D printing could add some value. Thanks so much. Definitely feel free to reach out to me via email as well if you have any more questions. I can take a look at some of the questions now. It seems like there's lots, so that's great.
Yeah, we got a couple common threads. I think you covered a lot of the questions on strength and qualification at the end there. But maybe just a quick one on generally with the customers that we've been seeing trying to replace cast parts. What are you seeing as far as testing that they're doing on those parts in order to verify the strength? Yeah, so similar to some of the results we looked at just before, a lot of our customers are printing parts, the same geometries that they would with their cast alternatives, and they'll run them through their instrons and they'll run them through tensile testing, as well as some of those lifetime testing that we looked at there. Then from there, actually, a lot of customers are then able to understand, okay, these parts are actually outperforming our cast components. How can we further optimize this geometry? And that's then when you can understand those. Maybe we don't need it to be as dense as it is. Maybe we can remove some material. Maybe we can add some latticing or things like that to actually further take advantages of these additive manufacturing benefits to reduce the weight as well as reduce the cost of the part and still get the properties we need for the application. So that's a really interesting thing to look at, is once you understand the properties of the part, you can really understand how to take advantage of those properties with the full benefits of the 3D printing process. Another common thread, materials that are available on the two systems, if you kind of break it down by system. Sure. So like I mentioned before, these processes are based off of metal injection molding, which is a industry that's been around for over 50 years. It produces billions of parts a year. If you have a cell phone, if you're holding a cell phone, if you're using a computer today, chances are pretty high you have a metal injection molded part in those machines. That being said, our processes are compatible with any material that's possible to metal injection mold. We use the same powders, we use the same process.
Granted, we do need to qualify those materials for our systems. Like I mentioned earlier on in the presentation, one of our goals here at Desktop Metal is to make these machines accessible and easy to use. What does that mean? It means that when we ship you a material, when you start printing a material, it's going to work the first time you use it. You're going to get the parts you need, the properties you need. So currently today on the studio system, on the shop system, we have just 17.4 pH stainless steel, very common stainless steel. It's great for a wide variety of applications, excellent mechanical properties, excellent corrosion properties as well. We're adding constantly more materials to that machine. We're working to produce them every day. We have a whole materials team here that's constantly verifying new powders. When it comes to the studio system, today we have 17.4 stainless steel as well. We also have 316L stainless steel, which is great for those corrosion environments and it's better at higher temperatures. We have H13 tool steel, which is great for those high hardness applications like molding applications, die casting operations, stamping applications. A lot of our tooling customers are very happy with their H13. 4140, a low alloy steel. And then we have copper material. We didn't talk too much about copper today, but we also have copper, which is great for those heat exchangers and electrical applications.
Awesome. And then maybe one more quick one to wrap it up. Could you talk a little bit about what design sort of rules and specifically some questions around, sintering, what you have to design for as far as sintering goes, especially in the shop system?
Sure. So with this process, right, you have to consider both printing as well as the sintering process. Printing, of course, is going to follow on the studio system is going to follow very similar guidelines to your FDM or FFF printing, where you have to ensure that your overhangs are supported, things like that, so that you're simply not printing on air. With the shop system, we're printing in a powder bed. So the parts are going to self-support themselves during printing because you have that powder underneath the part to ensure it's not going to topple. That being said, after printing, you're going to remove that part from that powder and you're going to put it into a furnace where it's going to get just below its melting temperature, and the part can then deform if it's not properly supported. So a couple of methods for that is you can print a support to ensure your part deforms predictably, and we also have a simulation product called Live Sinter. Live Sinter is going to take your part, it's going to predict that shrinkage, it's going to predict that deformation to understand if your part's going to be successful. It's also going to produce a negative offset of your geometry. So if you had an overhang, a bridge, it's going to actually cock that up into an arch so that during sintering, it's going to sinter to straight. So that simulation software really helps with understanding what's actually happening in the furnace, as well as ensuring that your parts come out to tolerance to the geometry that you're expecting and that you need. So yeah.
Great. I think that is a lot of the questions. And if there's any additional, plenty of specific questions still in the chat, but if you have those, I think reach out to Ethan.
Yeah, feel free to shoot me an email, sign up for a meeting with me. I'm always happy to chat. We didn't get to some, I'm looking through, there's some, very specific questions, things like that. Feel free to just shoot me a note. I'm happy to get back to you.